We're still here in work and energy chapter. We will talk more about potential energy today, and in specific, the reference regarding the potential energy. When you're talking about calculations related to potential energy, it is important to define your references. Reference point can be defined as a random chosen point for which the distance is measured. So let's say here we have a table, we have a shelf, and we have the ceiling. C for the ceiling, T for the table, and F is denoted for the floor. Now, from the equation we talked before that E, which is the potential energy, equals for the gravitational force mgh. So we discussed before that the change in potential energy delta E depends only on the change in height delta h. The value of h can be measured from any convenient reference point, and the potential energy will change according to that reference point, as long as the reference point is kept the same for all the measurements when solving a certain problem. So we know that change in height is important, and change in height will change the gravitational potential energy, and it is the same regardless of your frame of reference. So we can see here there's a book sitting on the shelf. The value of h for the shelf can be defined relative to the floor hf, and the potential energy of the book on that shelf relative to the table can be denoted using the height from the table to the shelf annotated as ht, and from the shelf to the ceiling annotated as hc. In this case, it's important to mention that hc will have a negative value because the height of the initial point is smaller than the height of the final point, as we will see in our example. So if you were trying to determine how much gravitational potential energy the book would lose as it falls from the shelf to the tabletop, then it is logic to use the tabletop as your reference point. You can always use whatever reference point you want, but it makes sense to choose the easiest reference point that can make you stumble upon the final answer as quick as possible. Gravitational potential energy. Change in gravitational potential energy depends on the change in the vertical height only. So the calculation of h in this example, you have a cart on an inclined surface in an angle of theta. Then you need to use a lot of trigonometry to be able to find the ratio. In this case, sine theta equals h over d, and you can find h or d or theta for whatever the problem is asking you to do. So the change in gravitational potential energy of the cart rolling down a frictionless ramp depend only on the vertical measurement and how far the cart is going away from the even surface. But of course, if you are solving a dynamic problem, as we saw before, it's a different story. But if you want to find the gravitational potential energy of the cart in this point versus the potential energy in this point, what matters is how high it is from the even surface, which is h1 in this case, or from this surface, which is h2. Let's say we have a toy car track set up on a tabletop. You can see the car can glide over this path. It is on the tabletop. We set the convention upwards is positive, downwards is negative. The problem is saying what is the gravitational potential energy of the car, which has a mass of 0.025 kilograms relative to the floor, and find the change in gravitational potential energy of the car when it arrives at the bottom of the hill. What is given? Mass of the car, gravitational acceleration, height at the first position, which is here, from the surface or from the floor, and height 2 when the car reach here from the surface or from the floor. So in this case, our main reference is the floor. Our second reference is the toy car. Firstly, we need to find EP1, and we need to find delta EP. To find EP1, which is the potential energy 1, would equal mass of the toy car by gravitational acceleration by h1, the height from the surface of the floor. That would give you 0.025 by 9.81 by 2.15 meters. Make sure you look up the units and make sure they're all consistent, because your final unit should be kilogram multiplied by meter squared over second squared, which is joule. Then the final EP1 would be 0.527 joules. And to find the change in gravitational potential energy, you need to find delta H, because delta E would equal mg delta H. Delta H is H2 minus H1, the height of the car from the surface of the floor at the second position minus the height of the car from the surface of the floor at the first position. That would be 0.95 minus 2.15. That would be in minus, which is normal, minus 1.2 meters. Delta EP equals mg delta H, 0.025 kilograms, the mass of the toy car, by 9.81, which you know, by minus 1.2 meters. Again, check in with the units. That would be kilogram multiplied by meter squared over second squared. That's the joules. So the delta EP would be minus 0.294 joules.